In section 1.4, we're going to talk about conventions for writing measurements. And I hope you've seen a lot of this in high school. I just think it's worth looking at it together to make sure that we have a common language and common jargon. If I were in front of you in a group, as usual, I would love to stop and solicit your input. I suspect you know the meaning of a lot of these terms. This format doesn't let me do that, but I hope I will pause and give you a chance to think about your own answers, and you can always pause the video if you need more time to think. The first thing I want to do is distinguish between qualitative observations and quantitative observations. And I'm going to illustrate that by applying it to the picture that I have here. This is me when I was younger, along with some of our lovely students. And I can make a quantitative observation, or in other words, I could make a measurement by saying I'm 5'8". It's a quantitative measurement. Because it has a number in it. So that's what distinguishes quantitative observations or measurements from qualitative observations. Qualitative observations have no number, and in this case I might say I'm tall. So let's see what conventions we're going to use to express measurements. There was a problem with what I just said. I said I was 5'8", and that's kind of meaningless without any units. So the first point we're going to look at is that we're all going to put units on our measurements. As you get to know me, you'll know that I don't want you to memorize things. I want things to make sense. I want us to apply things. So I'm never going to get you to list off the criteria for a good measurement. Instead, every time you write a measurement, you are going to include units. So maybe I should say, instead of that I'm 5'8", that I'm 5 foot, 8 inches. Now, sometimes that's a hard sell for students to put units on every quantity, but I have a story from the news from 1999 to hopefully illustrate why it's so important to include units. Back in 1999, NASA built and launched a Mars Climate Orbiter. And it was supposed to go into orbit around Mars and record the weather on Mars. But the MCO-MIB, the Mars Climate Orbiter Mishap Investigation Board, determined that the reason that this was lost is that the people programming it didn't know what units they were using. The programmers who programmed it thought they were using English units. The people that built the orbiter thought they were using metric units. And because often when you change from one measurement system to another, the numerical value changes as well, this was programmed for the wrong trajectory. It flew past Mars and never ended up in orbit, so millions and millions of dollars were lost. You're going to put a unit on every quantity. We are always going to use, well, you're usually going to use SI units or metric units. SI stands for System International or metric units. And here's a news story to show you why that's important. This ISMB stands for the Institute for Safe Medication Practices. And they were reporting on a story where a patient was given the wrong dose because the person prescribed 0.5 grains and the person who delivered the dose gave 0.5 grams. So what they decided is, like us, we should use SI units. Here is a table of SI units, and I think that you know 4 of these. I think you are fluent with meters, kilograms, seconds, and moles. Temperature in Kelvin we'll look at later in the course. Amperes and candelas we won't need in this course at all. The SI unit of length is a meter with the symbol M. The SI unit of mass is a kilogram with symbol kg. and the SI unit of time is a second with the symbol S. That's S, not SEC, and that's the way that it is. Why is that the way it is? Because I listen to the International Union of Pure and Applied Chemists. That's an international committee that gets together and decides on conventions, and they list them in various books. For units, you might be interested to check out the Green Book from IUPAC. So chemists use S. I remember watching Star Trek: The Next Generation years ago, and some of you may have seen it in reruns. The android in Star Trek: The Next Generation was named Data, and in one episode, someone called him Data. When Data corrected him, the person said, Data, what's the difference? And Data said, one's my name and one isn't. So that's exactly how I feel about it. One's the right unit and one isn't. Now, sometimes novice students in university are worried I'm going to take points off for things. I'm your mentor, I'm not your prisoner. If you write SEC, I'll fix it. I probably won't take marks off it, but I know you will want to do things the right way, and that's the way that we're motivated. The final unit that you know already is for the amount of substance, and the word is MOLE, and the unit is MOL without the E. Why? Because one's the symbol and one isn't. We can extend our list of units by using these prefixes. And based on my experience with first-year students, I think you are comfortable with milli, centi, deci, and kilo. I know that you know that a milliliter is 1/1000th of a liter, and a kilogram contains 1,000 grams. We might want to use this table later, but if we did, I would provide you with the conversion factor. So for example, if I wanted to use micro, I would have to tell you that micro was 1/1,000,000th. So back to my measurement of my height. To be an SI, I could say that I am 173 centimeters or 1.73 meters. Those would both be true. Which one is right? They both are. I could also say that I am 0.00173 kilometers tall. That doesn't make a lot of sense. Use your good judgment. This cartoon also comes from a long time ago. You can tell I'm getting a little old. It has milligrams and centigrams, and that's one reason I put it here. But another reason is that it shows cursive handwriting. I will also be using cursive handwriting when I read your written work, and if you can't read cursive writing, please let me know. I would hate to have you suffer in silence and not understand something that I'm doing. Recently, though, my understanding is that the students can read cursive writing even if they choose not to use it themselves. Generally, we use SI units, but sometimes we use derived units, and here are some examples. First of all, just as an example, a Newton is a unit of force. And I don't expect you to know this, but if you remember your physics, force equals mass times acceleration. So a unit of force would be a unit of mass times a unit of acceleration. Basically, it's SI, but when we say Newton instead, that's much more concise. Do I expect you're going to remember that that's what a Newton is? No, I'm using that for illustrative purposes only. The derived unit of a liter is going to be useful for you. Let's spend a little bit more time with that. A liter is a unit of volume. And liter is defined as the volume of a cube that's 1 decimeter on each side. The volume of a cube is its length times its width times its height. So 1 liter is defined as a cubic decimeter. For my purpose, though, it's going to be more interesting to express it in terms of centimeters. And I trust that you could figure out that a decimeter was 10 centimeters. So in other words, a liter is 1,000 cubic centimeters. You remember that the exponent applies to all the terms inside the brackets. In other words, this 1 liter cube contains 1,000 of these smaller cubic centimeter units. But there's another definition of a liter. That's in terms of milliliters. A liter is 1,000 milliliters. But if a liter is 1,000 cubic centimeters and a liter is 1,000 milliliters, then it turns out that a cubic centimeter is the same as a milliliter, and that might be useful to remember. Why 2 units of volume? Usually we use cubic centimeters for solids that are measured with a ruler. Milliliters are usually used for liquids, which you measure in, say, a graduated cylinder. Both are equivalent. You'll be able to go back and forth. In the next section, we will look at making measurements with the correct number of decimal places. In other words, we'll investigate significant figures.